A pot filled with water is placed on a perfectly flat sheet of black glass. There is no flame, no glowing heating element, and beneath the glass, nothing hot is touching the pot. Yet within seconds, the metal bottom begins to heat. The water quickly approaches boiling, while most of the energy appears to pass straight through the surface between them. Even more strangely, lift the pot away, and the production of heat stops almost immediately. So how does energy cross the glass without first heating it? Why can a metal pot become hot without touching a conventional heat source? And how does the machine know that the pot is there? The answer lies inside an electronic system designed to turn the cookware itself into the heating element. On a gas stove, a flame heats the outside of the pot. On a conventional electric cooktop, current flows through a resistive element. That element becomes hot, transfers heat into the glass, and the glass finally transfers it into the cookware. Every transfer takes time, and some of the energy escapes into the surrounding air. An induction cooktop works in a fundamentally different way. It does not try to create a hot surface beneath the pot. Instead, it sends electromagnetic energy through the glass and produces heat directly inside the metal base of the cookware. The pot is no longer just a container for food. Once placed in the correct position, it becomes the electromagnetic load that completes the heating process. But before that can happen, electricity from the wall must pass through a carefully controlled chain of conversion. Directly beneath each cooking zone is a flat copper coil, usually wound into a tight spiral. This coil is not a resistive heater. It is not supposed to glow red, and it does not need to heat the glass directly. Alternating current enters the cooktop from the electrical supply. A rectifier first converts it into direct current. Power transistors then switch that current on and off at high speed, creating a high-frequency alternating current for the copper coil. As the current repeatedly changes direction, it produces a magnetic field that also changes direction and strength. The glass ceramic surface above the coil is electrically insulating and does not respond strongly enough to become the main heating element. The changing magnetic field passes through it with relatively little energy absorbed. But the moment suitable cookware enters that field, the behavior of the entire system changes. The changing magnetic field penetrates the metal base and induces closed loops of electrical current inside it. These circulating currents are known as eddy currents. No wire connects the coil to the pot. No electrical contact passes through the glass. The current is created directly within the metal by electromagnetic induction, and metal has electrical resistance. As the induced currents move through the base, that resistance converts electrical energy into heat. This is the moment when invisible electrical energy becomes useful thermal energy. In ferromagnetic materials, magnetic losses can contribute additional heating, but the dominant result is the same: energy becomes heat inside the cookware itself. The cooktop has effectively moved the heating element from beneath the glass into the bottom of the pot. This is why induction can respond so quickly. Energy does not need to heat a coil, then the glass, and finally the cookware. Heat begins much closer to the food. But this creates one of the most common misunderstandings about induction cooking. The glass does not generate most of the heat, but that does not mean it remains cold. Once the base of the pot becomes hot, some of that heat flows back into the glass through direct contact. The area immediately beneath the cookware can still become hot enough to cause a serious burn. The important difference is the direction of the heat flow. On a radiant electric cooktop, the element heats the glass, and the glass heats the pot. On an induction cooktop, the pot is heated first, and the hot pot then warms the glass beneath it. When the pot is removed, electromagnetic heating stops. There is no glowing element beneath the surface continuing to release large amounts of stored heat. The glass and the cookware will still contain residual thermal energy, but no new heat is being generated in the missing pot. This is also why the region surrounding the cookware usually remains much cooler than the active cooking area. However, the system will not work equally well with every metal pot. To receive energy efficiently from a conventional induction coil, the cookware must have a suitable magnetic base. Cast iron works extremely well. Many types of steel also work. A simple test is to place a magnet against the bottom of the cookware. If the magnet attaches firmly, the cookware will usually operate on an induction cooktop. Copper, aluminum, and some grades of stainless steel do not couple efficiently with the conventional induction system when used alone. But cookware made from these materials can still work if the manufacturer adds a ferromagnetic steel layer to the base. That steel layer interacts with the magnetic field and generates heat. The surrounding aluminum or copper can then help spread that heat more evenly across the bottom of the pot. The shape of the cookware matters as well. A flat base allows consistent positioning above the coil. Its diameter must overlap enough of the active magnetic region, and the pot should remain close to the center of the cooking zone. If it is too small, badly positioned, or made from an unsuitable material, the cooktop may refuse to activate. But there is no camera looking through the glass. The machine detects the cookware through the same coil that transfers energy into it. Without a pot, the coil and its resonant circuit have a predictable electrical response. When ferromagnetic cookware is brought close to the coil, it becomes an electromagnetic load. The coil current, effective inductance, energy loss, and behavior of the resonant circuit all change. The controller can send a short test pulse through the coil and measure the response. If that response matches suitable cookware, the power circuit is allowed to begin normal operation. If no acceptable load is detected, the inverter remains off. If the cookware is too small or incompatible, the cooktop may display a warning and disable that zone. During cooking, current sensors continue to observe the electrical load. When the pot is lifted away, the response changes. The controller recognizes the missing cookware and stops transferring power. This safety behavior is not based on temperature alone. It comes from continuously watching how the cookware changes the electrical behavior of the coil. But detecting the pot is only the beginning. The cooktop must also control thousands of watts without overheating the food, the coil, or the power electronics beneath the glass. The user does not directly select the temperature of the copper coil. Instead, the control system changes how much power is transferred into the cookware. Depending on the circuit design, it can adjust the switching frequency, the duration of each switching event, or the periods during which energy is delivered. At high settings, power may be transferred almost continuously. At lower settings, some cooktops deliver energy in shorter cycles separated by pauses. Temperature sensors beneath the glass monitor the cooking zone and help protect the coil and electronics from excessive heat. Current sensors protect the power transistors from abnormal electrical loads. A cooling fan moves air across components that must repeatedly switch large amounts of electrical power inside a very thin enclosure. If the system detects excessive temperature, overcurrent, unsuitable cookware, or another unsafe condition, it can reduce power or shut the cooking zone down. The quiet surface above hides a machine that is constantly measuring, calculating, and correcting its own behavior, and sometimes, that hidden process can be heard. A changing magnetic field can cause the base of the cookware to vibrate slightly. If the bottom contains several bonded layers, each material may respond differently, producing a faint buzz, hum, or high-pitched sound. The exact sound depends on the cookware, its construction, and the selected power level. At lower power settings, energy delivery cycles may make the sound more noticeable. The cooling fan can add another source of noise beneath the surface. These sounds do not mean that energy is heating the pot through the air. They are mechanical side effects created by the cookware, the alternating magnetic field, and the cooling system. The diameter of the coil also influences where heat is produced. The strongest coupling occurs above the active coil. A very large pan may therefore develop a hotter region near the center if its base cannot spread heat evenly. Induction does not eliminate every limitation of cooking. It changes where the heat begins and gives electronics for greater control over how the energy reaches the cookware. Beneath that simple black surface is a complete chain of energy conversion. Alternating current enters the cooktop. A rectifier converts it into direct current. Power transistors create a high-frequency electrical signal. A copper coil turns that signal into a changing magnetic field. The field passes through the glass and induces currents inside the base of the cookware. The resistance of the metal converts those currents into heat, and that heat flows directly into the food. The glass has not disappeared from the process, but it is no longer the primary source of heat. The pot becomes the heating element. The copper coil transfers energy, detects the cookware, and gives the control system the information needed to regulate power safely. There is no flame, no glowing resistance wire, and no direct electrical connection to the pot. Only an invisible magnetic field turning an ordinary piece of metal into a precisely controlled source of heat. And that is how an induction cooktop heats the cookware while largely bypassing the surface directly between the coil and the pan.